Reduction of FFLGN, the most attractive feature of FFLGN is the thermal reduction of graphene-like sheets, as a result of which oxygen-containing functional groups are removed. Whereupon its electrical, optical, and other properties change. Also, a reducer sheet of FFLGN is usually considered as one of the types of chemical produced graphene and has a number of other names, such as functionalized graphene, chemical modified graphene, chemical transformed graphene, or reduced graphene. Currently, the properties of pure graphene and reduced FFLGN are close. Moreover, the reduction of FFLGN is one of the actual processes that allows obtaining graphene-like materials in large quantities, and their application is important in science and technology. In this regard, to obtain graphene and large quantities, the following methods of reduction process are used: chemical, thermal, and electrochemical. As mentioned above, the use of these methods leads to obtaining FFLGN, which electrical, thermal, mechanical properties are close to graphene. Various chemical reagents are used in chemical reduction processes, but one of the most common is hydrogen monohydrate, which is a good chemical reagent for the reduction of FFLGN. The processes of reducing FFLGN with hydrogen and its derivatives, such as hydrogen and dimethyl hydrogen hydrate, is the addition to the aqueous dispersion of FFLGN. FFLGN can be reduced by heat treatment, and this process is called reduction using thermal annealing. Thermal annealing is usually carried out by thermal radiation. Some non-standard heating means, such as microwave irradiation and photoradiation, for the thermal reduction are used as an alternative. Also, the main advantages of microwave radiation compared with conventional methods of heating is to heat the substance evenly and quickly. In addition to the above methods, thermal reduction in a flue tube in various atmospheres, argon, vacuum, hydrogen, argon is currently widely used. Another method that shows reduction of FFLGN relies on the electrochemical removal of oxygen-containing functional groups. Electrochemical reduction of FFLGN sheets or films is performed in an electrochemical cell using an aqueous buffer solution at room temperature. Reduction, as a rule, does not require a special chemical and is mainly due to the electronic exchange between FFLGN and electrodes. One of the important points in the process of temperature reduction of FFLGN is temperature zones at which functional oxygen-containing groups are removed in a hydrogen stream in a flue tube under the influence of various temperatures. The process of temperature reduction of FFLGN to 2000 Celsius degree has 6 important temperature zones: 140, 180, 600, and 800 to 1000, and 1000 to 2000. At a temperature of 130, due to the mild evaporation of intercalated hydrogen molecules, a continuous intensive compression of Joule crystal occurs. In the range of 140-180, rapid evaporation intercalated hydrogen molecules. Joule crystals are partly accelerated, and in the range of 108, the layers of all types of graphene and Joule are contracted with removal of basic carboxyl groups. Within 600, the residual carboxyl and particle hydroxyl groups are removed as gases. Within a range of 800, residual hydroxyl and particle epoxy groups are removed. In the range of 1000, decrease in the number of defects is observed. Thus, the difference of FFLGN and reduced FFLGN is that FFLGN has a highly oxygenated and with presence of many oxygen-containing functional groups that are smaller in reduced FFLGN. These oxygen-containing functional groups, such as epoxy, hydroxyl carbon, and carboxyl groups on its main plane, can be removed in the process of chemical and thermal reduction, as a result of which the physical chemical properties of reduced FFLGN are changing and can also find wider application in science and technology. The experimental part of the synthesis and the study of the optical and electrical properties of FFLGN films, and also changing the structures of FFLGN membrane after thermal reduction are given in sections, and application as a humidity sensor based on the FFLGN membranes is discussed in next sections of this work.